Already we have seen I mode, P mode of a PID controller. Now let us see the derivative mode of a P controller, PID controller. This the expression for PID controller, M of T equal to Kc multiplied by E of T plus Kc by Ti integral of E of T dt. These two are for P and I mode. Plus the derivative mode is Kc Td d by dt. This is proportional to this portion is proportional to rate of change of error. Suppose you are having time versus error plot. The error is increasing like this means slope, that is slope is d by dt. Here m d of t is proportional to d by dt. It means what? Suppose slope is higher. Suppose slope is higher. The future error for this will be error for this will be this E1 will be higher than E0. Future error for this will be higher than E0. If you compare E1 and E0, E1's future error will be higher because the rate at which it increases is higher. That's why we have to take necessary action now to avoid future error. That is called anticipatory control. Therefore, the derivative mode simply D mode is called anticipatory controller. It will anticipate the future error so that it will take action now. Where and all it will be useful? Suppose the system, the process has large dead time. And large time constant. And it has large lag. So these type of systems, anticipatory controller is required. But this d by dt, when set point equal to PV, once the process is settled, set point equal to PV and E of t equal to 0, that time we are expecting that the cross variable will be like this. Since set point equal to PV. Like this we are expecting, but it is not so. Actually, it will be like this. This is because of noise superimposed on that. We know that noise is inevitable because in electronic circuit, noise is noise because of Ohm's law. Ohm's law states that voltage is directly proportional to current for a constant temperature, but temperature is not constant. It is wandering around some value. That's why this voltage varies. That's why all electronic circuit will generate noise. That's why you cannot expect a cross variable like this. This is ideal case. Ideal. But in practice, it will be like this. This is PV. That's why the slope of this noise often varies. That's why the derivative controller will act as a disturbance to the process. It will disturb the process because its output is function of slope of the signal. The slope of the noise signal will be like this. Slope will be positive, negative, always it is changing. That's why this will disturb the process. That too, particularly set point equal to PV, it will affect the process. This can be solved by using the controller this way. What is dE by dt? dE by dt is d by dt of set point minus PV. But set point is constant. That's why this is equal to 0. Therefore, d by dt can be written as minus dPV by dt. So, for a zero signal, noise is a dominating signal. Noise is a dominating signal. Noise is a dominating signal. Signal. If magnitude is very small, if magnitude is very small, when the magnitude of error signal will be small, set point equal to PV, the time error equal to 0. That's why noise alone will be there. That noise will be amplified. That's why there will be a switch. Derivative mode on-off switch will be there in the PID controller to turn off the derivative mode whenever the process is settled, because it unnecessarily will introduce a disturbance in the process. This can be solved. Instead of implementing d by dt, we can implement dPV by dt. That's why the controller will be implemented like this. Set point here only P plus I alone is implemented. Then the process is there. The output is taken and a derivative mode is used here. The output will be added to this PID control. So here input to the D controller is PV, not error. So this minus sign is here, so that what we can do is here we can put the minus sign. So that's all. So instead of implementing the D mode for error, it is implemented for PV, so that the amplification of noise can be reduced. Anyhow, cross variable will be superimposed with the noise, but its amplitude will be higher while compare with the error signal. That's why this can be ignored. Let us see the simulation for here. To simulate and test the I mode of PID controller, we consider a fourth order process. That is 1 by s plus 1 to the power 4 is considered. For that, we are taking comparing P only controller. For that, we entered the tuning parameters of P controller, that is the ultimate gain of 4 multiplied by 0.5. This is P only controller. Second one is PD controller. The derivative mode is included here. Here, the proportional gain is 4 multiplied by 0.5, 0 integral time Ki. Kd is 4 multiplied by 0.5 multiplied by 6 by 8 Td. So far that, let us simulate. Now let us simulate up to 50 servo response. After that, it is a regulator response. You notice that this yellow is P only controller. Since it is a P only controller, a set point change of 1 is given, but it is settled at 6.5. The blue is PD controller, proportional plus derivative controller. Note down the raise time. Raise time is improved. Raise overshoot, you notice that less overshoot. Settling time, you notice quickly settled. Decay ratio, fast decay ratio, that's why it is quickly settled. It's settled within 20 seconds. In 15 seconds, it is settled. But the P only controller settles only about 30 seconds. For servo response, regulatory response, if you consider that is given at 50 seconds, overshoot is less, quick settling time, fast decay ratio. So derivative mode improves the response. It quickly settles. Why? Because derivative mode is an anticipatory controller. That's why it anticipates future error and takes necessary action. That's why quickly settles. That you can notice. Now let us check for P and PID. PID means 0.64 multiplied by 0.6 for proportional. Integral time is 4 multiplied by 0.6 multiplied by 6 TU divided by 2. Derivative mode is 4 multiplied by 0.6 Kc. TD is 6 divided by 8. Then that's all. Kc TD. Now here let us enter only for PI. PI means point. PI means 0.45. 4 multiplied by 0.45 multiplied by 6 divided by 1.2. Yellow is PID, blue is PI controller. You notice that for if inclusion of derivative mode improves the raise time, less raise time. Overshoot is almost same, but PI has less overshoot, of course, but not appreciable difference. But for PI controller, large undershoot is there. But in a derivative mode, because of anticipatory controller, there is less undershoot. Settling time is very much improved. Decay ratio is improved. So less ISEAA. That also you can notice. For at 50th second, we gave a disturbance to the process. Less overshoot for PID controller. While compare with the PI controller, less overshoot, settling time is better, decay ratio is better. Decay ratio is very much improved. So derivative mode improves the settling time, raise time, overshoot. So these are the advantages of using derivative mode. So now, what are the advantages of derivative mode? Advantages: less overshoot, less raise time, less overshoot, less raise time, settling time less, less settling time. These are the advantages that we have seen. What is the disadvantages? Disadvantages it amplifies noise. This is the disadvantage. That too, particularly once process is settled, the noise will be amplified. That is the disadvantage of. That's why there will be a switch called on-off switch for derivative mode. Whenever process is settled, the D mode will be put off to avoid amplification of noise.